A very good morning to one and all. Today we have with us Dr. Manish Gupta sir. So sir is a senior director at Google DeepMind. He is leading AI research team across India and Japan. Previously, sir has led VideoCan, an AI startup, and the research centers for Xerox and IBM in India. As a senior manager at IBM, TJ Watson Research Center in Yorktown Heights, New York, he led the team developing system softwares for Blue Gen slash Elk supercomputer. IBM was awarded a National Medal of Technology and Innovation for Blue Green by the then US President Barack Obama in 2009. So Manish sir holds a PhD in computer science from the University of Illinois at Urbana. He has co-authored about 75 papers with more than 8,000 citations in Google Scholar and has an H index of 49 in the area of high performance computing, compilers, and virtual machine optimizations, and has been granted 19 US patents, while at IBM, Manish sir received two Outstanding Technical Achievement Awards, an Outstanding Innovation Award, and the Leo Gardner Team Award for Client Excellence. Manish sir is a fellow of ACM and the Indian National Academy of Engineer and a recipient of Distinguished Alumnus Award from the IIT Delhi. So over to you, sir.
Thank you for the invitation. So I'll be talking about the uh, transformative power of AI. Again, we are in this very interesting era when uh, computing and AI in particular is pretty much transforming every industry, every aspect of how the world is run, and also some open challenges. Uh, so I'm from Google DeepMind, where our mission is to build AI responsibly to benefit humanity. Uh, Being in India, where there's a pretty significant part of humanity lives, this is one part which we take very seriously, which I'll cover in the second part of my talk. And one of the areas that I want to highlight before getting into more mainstream kind of work on foundation models is this potential for AI to help accelerate scientific discovery. And one of the key kind of milestones in this signaling, right, the potential, in fact, came from this work on AlphaFold at Google DeepMind, uh, for which there was a Nobel Prize in Chemistry that was awarded to Demis Hassabis and John Jumper from Google DeepMind last year. Uh, we all know from our high school physics that proteins are the building blocks of life, and uh, they uh, comprised of chains of amino acids that fold into a unique shape, which is what gives the protein its distinctive properties. And for a long time, uh, predicting the structure of a protein whose structure wasn't previously known was a huge, cumbersome, and time consuming process. It would take typically about 3 to 5 years of research, equivalent to a PhD, to uncover the structure of a single protein. And uh, there used to be this biannual contest, CASP, where for newly discovered protein structures, they would be posed as a test to various software models, which would compete to again predict the structure of those proteins. And uh, AlphaFold pretty much kind of uh, in 2019, the entries that were submitted by AlphaFold, they were close enough to the actual known structure of those proteins that the community basically considered the problem solved. And today, all of what the team did was they basically uh, made predictions of all 200 million proteins known to humankind and made them freely available to researchers. So, that's equivalent to almost like a billion PhD years equivalent of work that was accelerated by AI in less than a year. And today there are over 2 million researchers across the world, including, I've been told there are over 150,000 researchers in India who are using AlphaFold on variety of problems, ranging from, of course, drug discovery is a key problem, but also things like uh, designing an enzyme to make plastics degradable. So, so, and AlphaFold is just one example. We have seen dramatic kind of breakthroughs in many areas traditionally associated with science uh, through the use of AI. So today, AI-based weather forecasting models from Google DeepMind again are producing higher quality weather forecasts than traditional physics-based models, and are being used even for things like cyclone prediction, typhoon prediction. Um, in areas like clean energy, where fusion holds the potential to uh, create like a really clean form of energy, where uh, it's based on nuclear energy, but unlike fission, it doesn't lead to radioactive waste being produced. Uh, but the problem with fusion so far has been that it takes more energy to get a controlled fusion reaction going uh, uh, in a lab setting. Of course, all of our energy on Earth derives from the fusion that's going on the sun. But in a controlled setting, uh, we end up putting more energy to get a fusion reaction going than we get out of it. And again, researchers are confident that in the next 2 to 3 years' time, we are likely to reach that break even point when you get more energy out of that controlled fusion reaction than what you put into it, uh, which again has the potential to unlock uh, a really, really kind of boundless source of energy. Uh, so, so with that, let me move to the more mainstream parts uh, uh, of the work on AI, starting with a kind of a quick history of uh, deep learning, which over the last 15 years became the dominant paradigm within AI. And then within AI, as you all know, machine learning is the part of AI which really took off and became the dominant part of AI. And then I'll talk about the more recent trend over the last 5 to 7 years that we have seen of foundation models, which is the new paradigm within deep learning, which is becoming dominant. Um, Talk about AI being applied for problems like synthesis and creativity. In particular, if you go back 10, 15 years ago, even experts were predicting that AI would be used to automate a lot of uh, mundane kind of re- repetitive tasks, and creativity will remain this uniquely human endeavor. Uh, and again, we have been surprised by uh, how uh, AI models are now uh, doing quite well at a lot of these creative tasks, helping human artists um, as well as uh, kind of people at large. Then I'll talk about our work in particular in our team in Bangalore on inclusive AI. How do we develop AI in a manner that really works for everyone, and in particular brings the benefits to billions of people who have previously not been touched by AI? And finally, some open challenges and takeaways. And again, I mean, if at any point you would like to ask a question, of course, you can ask questions at the end of the talk. But if you'd like to uh, interrupt and ask questions, happy to. Maybe you can give some indication. Sorry, I'm not there in person, but you can give some indication, and happy to stop and answer any questions you have at any point during the talk as well. Okay, so I'm sure all of you are already kind of familiar with artificial neural networks, with deep learning, which is this kind of modern reincarnation of the old concept of artificial neural networks, which was loosely inspired by how human brain works. And the equivalent of neurons in this case are these very simple mathematical units shown in this diagram through those little circles or little ovals. Uh, and these could be basically now trained, these networks could be trained. And by training, kind of what we mean is you come up with the values of those parameters, right? So many of these mathematical units, they could be doing as simple computation as multiplying the input by a weight, adding an offset term, and passing the output to the next layer. And what we know is uh, theoretically, right, we know that even a two-layer deep neural network can approximate any computable function, right? So that's the universal approximation theorem uh, uh, that's been developed. And in practice as well, what we have seen is these networks, they made a comeback around the year 2011 on this problem of image classification, where again, given an image, can you automatically, for instance, on this image shown on the top left, that this is an image of a leopard, can you have a model uh, automatically identify the dominant object in that image? And on that problem, there was a deep learning based algorithm based model which showed a dramatic increase in accuracy relative to previous models um, on this MNIST competition. And soon, and that really marked the arrival of the deep learning kind of a trend, deep learning era within machine learning. Uh, and soon after that, on a variety of other problems like speech recognition, right, where you take this signal and you kind of identify what are the words that are spoken um, uh, as part of that speech. So this was again, automatic speech recognition was a problem that the research community had worked on for decades already. And there were models that were combining language model, acoustic model, kind of cascaded together to give you these speech recognition models. And soon you saw that after that image recognition, image classification breakthrough, researchers trained another deep neural network with millions of labeled audio samples uh, uh, with labeled data on what was the actual text that was spoken uh, in those audio samples, and simply did trained a neural network end to end, right, using without bothering to go into what languages is what is the acoustic model and so on, just simple kind of based on input and output, uh, where you have where you had training data uh, with those labels, and simply trained the network to, and it started doing better than some of the traditional models. Similar thing happened with the problem of machine translation, where you're taking a sentence in English here, translating that into French. So again, millions of parallel sentence pairs, when they were kind of fed to these deep neural networks, they started doing a better job at translation than the traditional machine learning based approaches. Yeah, and finally, even the reverse. And then even a comprehensive version of that image classification problem, where given an image, you're not just saying what's the dominant object in that image, you're describing that image similar to how a human might describe. Uh, and machine learning models started doing better. And of course, now you all have seen that even the reverse is becoming uh, possible, where you simply provide a caption, uh, text description on the right side, and the model will generate an image uh, that conforms to that description. Uh, so, so this first phase of deep learning kind of was quite transformative for this area, where pretty much for most of these uh, tough problems, deep learning based methods started becoming the best models at solving those problems, overtaking other machine learning based approaches. But still, there was something, couple of things that were still not very satisfying about this. Uh, One was that you typically needed lots of label data to train these networks. So often you needed to have millions of data points which had to be annotated uh, to train those networks. And second, for every problem, a new network had to be trained from scratch, uh, which is not how we humans deal with problems. Given a new problem, we don't start solving it from first principles. We apply our years of experience as well as, in particular, how we have solved similar problems as a starting point to solving a new problem. Uh, so, so this is what uh, this new era of new approach of foundation models ultimately enabled. And one of the key uh, research breakthroughs that enabled this was this transformer architecture that was presented in this famous paper, Attention is All You Need, at NeurIPS 2017. And uh, and and to see kind of how it was used, let's take the example of BERT, which could be argued as one of the first foundation models uh, that was created before the term foundation models was even coined. Uh, so, so to train BERT, what the team did was they took a lot of this text from sources like Wikipedia, digital books, freely available uh, data on the internet. And what they did was they took this self-supervised learning approach, where instead of having to label all of this data, they masked out 15%, roughly 15% of the words, and 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 started training this model BERT to predict those missing words. So kind of this reminds me of this fill in the blanks exercise that my English teacher would give me in school, and I'm sure many of you would have gone through similar fill in the blanks exercise while learning languages. Uh, and and to predict those missing words, BERT would look at kind of surrounding text in the context window, uh, and uh, and it would then use the transformer architecture, which would automatically kind of assign appropriate weights, paying more attention to, so for instance, to predict this word born, uh, the words Obama, 1961, Hawaii, kind of, in some sense, you need to pay more attention to those words than perhaps a lot of the other surrounding kind of words in the surrounding text to predict that word. And the transformer architecture allowed you, enabled you to kind of uh, uh, in an automated manner, uh, figure out the right weights such that you were able to make those predictions. And not only was BERT able to then make those predictions, similar to how when our teacher would give the fill in the blanks exercise, they were testing our ability to A, understand the language, and B, reason about things from surrounding context. Similarly, the act of predicting those words also gave the BERT model basic ability to kind of uh, start mastering the nuances of the language. And so it wasn't just for predicting those missing words on a whole bunch of natural language processing problems, ranging from things like sentiment analysis, which is a very common problem. Somebody is posting things on social media. Brands want to know, are they saying good things or bad things about my brand? Uh, or question answering, given a passage of text, can you answer a question? Or summarization, given, again, a piece of text, can you summarize it in a more concise form? So on a fairly broad range of these natural language processing problems, BERT started to uh, give you better results than those specially trained kind of uh, models for many of those problems. So, and fast forward to the next major foundation model that was built at Google was called Palm. It had 540 billion parameters. So this was built over 3 years ago. It almost now sounds like ancient history. I mean, things are progressing at such a fast pace in the field. So for Palm, the team did a comparison on 58 benchmarking tasks. They compared the performance of Palm with the best known model for each of those 58 tasks, uh, and and did this relative quality comparison. And you can see on this again, these bars with gray color, these are the ones where Palm does better, and the ones with this yellowish orangish color, this is where the specialized model did better. So you can see that while on some benchmarks the best specialized model did better, on a vast majority of tasks this one model, Palm, started doing better than those specialized models. And this is it is results like these that led the researchers at Stanford to coin the term foundation models. That now, when you want to solve a problem, instead of building a specific model for that problem, right, a new network from scratch, you can make use of these foundation models, which are pre-trained models, which are pre-trained based on self-supervision on large volumes of text, and they are able to do a better job than those specialized uh, models that were being built. And the other very interesting thing that the researchers saw after they built Palm, that it was also able to solve some mathematical puzzles, uh, but only if you gave it similar examples of mathematical problems, and not just similar examples, you also showed the model how to solve those problems. So for instance, if you have this problem, John takes care of 10 dogs, each dog takes half an hour to a day to walk. How many hours a week does he spend taking care of dogs? Now the model would fail to solve this problem if all you gave it was other kind of problems and the answer. But if you, in addition to that, to similar kind of problems, you also gave, in some sense, this model a step-by-step way of solving the problem, then the model is able to apply a similar kind of a step-by-step process for other problems. And you can see that between these two problems, right, John takes care of 10 dogs and Sean has 5 toys, uh, the two problem descriptions are not syntactically very similar. They're only semantically kind of, they require a similar kind of an approach, but syntactically they're very different. And despite that huge difference syntactically, the model is still able to take advantage of kind of having solved a similar problem to solve a new problem. So this they call chain of thought prompting. And this has become, again, a very, very powerful mechanism which is being used today by models uh, to kind of uh, uh, to solve many of these problems that require reasoning. And the other thing was that this approach wasn't just working for text. Researchers found that similar approach worked with other modalities, like images, for instance. So the traditional approach in applying AI to medical imaging was to, for instance, you're trying to build a model from chest X-rays, you're trying to build a model to predict kind of, is this a case of lung cancer? Or from mammography images, you're trying to see if is this a case of breast cancer? So the traditional approach in AI for medical imaging has been to build basically large data sets of labeled data and use supervised learning to build those models. And again, what the researchers found that if you started with even larger volumes of even unlabeled medical images, and you created a using self-supervised learning, if you built if you had models that built representations of these images, and then you fine-tuned those models with even relatively smaller amounts of labeled medical image data, you started to get better quality, you started to get better robustness in those uh, models. And similar thing our researchers found with things like speech data, even all of these other modalities as well, including speech. So for years at Google, we used to build speech models for each language separately, using often you needed sometimes over 100,000 hours of labeled speech data to build the model to build an acceptable quality model for a given language. And now, by taking this approach and building a model with trained on millions of hours of unlabeled speech data, and then you fine-tuned it with even, let's say, 1,000 hours of labeled speech data for a given language, you started to get higher quality uh, for that language than uh, a model built with very, very much larger amounts of labeled data. Which then brought us to this era of foundation models going commercial. Of course, it started with OpenAI launching a GPT based conversational assistant called ChatGPT, which has become very popular. And Google has been working on this model called Gemini, which is now the foundation model at Google, which is beginning to power a whole broad range of Google products, ranging from Google Search to the conversational assistant, also called Gemini, previously called Bard, also kind of how we do image search in products like Google Lens, how we do speech recognition. So all kinds of products which are now at Google being powered by this one model, Gemini. And what I'd like to show is a few kind of key features of Gemini. This is not meant to be like apologize if this comes across as a marketing pitch, but the intention is to share kind of capabilities of today's AI models and show how powerful they become. So let's look at so in Gemini 1.5, which was launched about a year and a half ago, or maybe less than that, February of last year, a few key capabilities that we introduced were A, multimodality, and B, long context window. Ability to handle a context window of 1 million tokens initially, and then later changing to 2 million tokens. And you can, and this 2 million tokens roughly corresponds to maybe of the order of, let's say, 1.5 million words of text in a language like English, something like 2 hours of video. So through this long context window capability, you could take fairly large amounts of text as part of your input question. And even if the model has not been trained on that data, it would be able to analyze all of that data in that question and answer questions. So let's take a look at one such capability on video data.
This is a demo of long context understanding, an experimental feature in our newest model, Gemini 1.5 Pro. We'll walk through a screen recording of example prompts using a 44-minute Buster Keaton film, which comes out to over 600,000 tokens. In Google AI Studio, we uploaded the video and asked, find the moment when a piece of paper is removed from the person's pocket and tell me some key information on it with the timecode. This screen capture is sped up, and this timer shows exactly how long it took to process each prompt. And keep in mind that processing times will vary. The model gave us this response, explaining that the piece of paper is a pawn ticket from Goldman & Company pawnbrokers with the date and cost, and it gave us this timecode 1201. When we pulled up that timecode, we found it was correct. The model had found the exact moment the piece of paper is removed from the person's pocket, and it extracted text accurately. Next, we gave it this drawing of a scene we were thinking of and asked, what is the timecode when this happens? This is an example of a multimodal prompt, where we combine text and image in our input. The model returned this timecode, 1534. We pulled that up and found that it was the correct scene. Like all generative models, responses vary and won't always be perfect. But notice how we didn't have to explain what was happening in the drawing. Simple drawings like this are a good way to test if the model can find something based on just a few abstract details, like it did here. These are just a couple examples of what's possible with a context window of up to 1 million multimodal tokens in Gemini 1.5 Pro.
So you can see again how Gemini is able to analyze these videos and answer all of these questions. And a lot of these capabilities are now being brought to things like YouTube, where again, those YouTube videos could be analyzed and you could ask questions, as well as they are being applied to online meetings. So today, at least at Google, it's become pretty standard practice for the meetings to be recorded, and then Gemini automatically takes notes. Those are based more on for meetings, it uses the transcript information, but it automatically starts to create a whole bunch of meeting notes that summarize what was discussed in the meeting, some of the action items, and so on. So we are beginning to see, again, models being used for a lot of these kinds of purposes. And then in December of last year, Google announced then the Gemini 2.0 model, where we introduced some of these agentic capabilities. Let's take a quick look.
Gemini 2.0 enables new kinds of multimodal AI agents. Agents that can see and hear the world around you. Think, plan, remember, and take action. Gemini 2.0 is what enables Project Astra, our research prototype of a universal AI assistant. Using capabilities like multimodal memory and real-time information, it lets you understand your world, live.
What can you tell me about this sculpture?
The sculpture you're seeing is called My World and Your World by Eva Rothschild, located in Lewis Cubitt Park in London.
What kind of themes does her work explore?
She creates abstract sculptures that invite viewers to interact with and interpret their surroundings in new ways.
Project Astra is multilingual, using native audio to seamlessly switch languages as you speak.
Est-ce que tu peux me dire quelque chose d'intéressant à propos de ces lanternes?
Bien sûr, je peux vous parler des lanternes. Les lanternes que vous voyez font partie de la porte d'entrée de Chinatown à Londres. நிச்சயமாக இது லண்டனில் உள்ள Chinatown நுழைவாயில்.
We're taking this to the next step with Project Mariner, with agents that can complete tasks on your behalf. You can ask it to do things like this that require multiple steps: doing research to look up the artist, then finding the painting, and then shopping for the right supplies. The agent uses the web to take action and find what you're looking for. It plans and reasons at each step, always staying in your control and completing your task. Gemini 2.0 enables agents that can be applied across domains. We're exploring agents that can explore virtual worlds, assisting you in video games.
Where do you recommend I attack from on this base?
Given the base layout, I recommend attacking from the bottom or south side. This direction allows you to target the town hall directly with your giants, while the wizards can handle the surrounding defenses.
Gemini 2.0 can reason about the physical world, understanding 3D spatial environments and objects. These capabilities are being applied to robotics, with agents that can assist you in your everyday physical environment. Learn more about how Gemini 2.0 is enabling the next generation of multimodal AI agents at deepmind.google/Gemini.
So, and more recently, a few months ago, we launched Gemini 2.5. And 2.5 has pretty much like captured the leadership position on a lot of different benchmarks, including many benchmarks for coding. And again, this video shows some simple examples where you can kind of just show it instructions at a very high level and generate code to again give you that similar output. And this has also led to popularization of this term called, now there is all of these models, not just from Google, there are also very powerful models from Anthropic, OpenAI, which are helping now software engineers do programming using what is now called vibe coding, right? Where you, instead of using a programming language, you simply describe kind of what you want to achieve using simple language, simple English, and then the model generates a very nice starting point for you for the code for accomplishing that task. One of the areas that we are extremely excited about is the potential for, again, earlier I showed that research prototype called Astra, which is our vision of how a universal digital assistant, right, can be built based on these powerful AI models. A universal assistant which is available to each and every one of us to help us with different aspects, right, of the kind of tasks we require help with. And one of those tasks would be learning. So we are really excited about the potential for these universal assistants to help each of us learn more effectively. And learning is going to become kind of a lifelong requirement, right? It's as you all would recognize, even as you graduate, right, from NIT Karnataka, which is again one of the top institutes in India, you cannot afford to let your learning stop. You'll have to keep learning well after graduating, just like people like me have been doing in order to even survive, right, to be able to do our jobs. So let's take a look at what Astra can enable in terms of helping us with learning.
Can you help me out with question number 39 here?
Of course. Is this the problem?
Yes, I don't really understand what to do here.
No problem. Let's take this to the blackboard. The key concept here is optical isomerism.
Got it. But how can I tell if an isomer is optically active?
Optically active compounds require a chiral carbon atom. A chiral carbon is one that is bonded to 4 different groups.
Okay, awesome. That makes sense. So how do I apply that to solve this problem?
Let me walk you through the steps to solve this problem.
Okay, got it. Let me find the structures first.
Sure, no worries. Feel free to show me when you're done.
I found 4 carbon chain structures. Is that correct?
Close, but not quite. There are 4 structures, but you've made a small mistake in the 3rd structure. Can you check your work again?
I can't actually find the mistake. Can you show it to me?
For sure. You added an extra hydrogen bond to the 2nd carbon atom. I'm circling it now.
Oh, okay. Good catch. That's actually really helpful. Thank you. So I think this is where the chiral center is. Can you confirm?
Yes, here is the chiral center. Well done.
Remember the optically active isomer problem we were working on? Can you show me what the 2 chiral molecules actually look like?
Sure. Have a look at the molecular structure. I've created the molecular structures of the 2 optically active isomers, also known as enantiomers of 2-bromobutane.
Thanks for all your help, Aston.
So again, I mean, I'm not going to claim that this model will work equally well on every problem that you throw at it, but the fact that it even works, right, on even these cherry-picked examples, at least I find quite quite impressive. And this whole goal, holy grail that we've had, right, in the edtech area of a personalized tutor that is available to each and every one of us to help us with our learning journey, it now very much seems to be within sight. Uh, uh, and now, switching gears, let me talk about again some of the areas. So far, we've been talking about applications of AI to various kinds of understanding related tasks, where it is helping us solve problems, understand different things. Let's look at how these models are also helping us with tasks that require creativity. And today, we are all beginning to use these models for tasks ranging from creating emails to documents to presentations with beautiful images to videos. Uh, and and from Google, one of the areas that we had pioneered was diffusion models to really which have been leading to very high quality text to image generation models. And again, for a while, kind of even after inventing diffusion models, uh, kind of Google wasn't quite kind of, there were other models which had taken over in terms of leadership. But starting with some with the Imagine 3 model launched about a year ago to then Imagine 4, we've seen again some very, very impressive advances in the kind of high quality images that these models are able to generate. And what I've shown here are some examples of images that have all been automatically generated by this Imagine 4 model. And we've also announced the VO3 models that now for the first time to video generation, it now brings audio capabilities as well. So we are no longer talking about from the text description, silent videos that have traditionally been generated by the AI models, but now even videos with audio. So here are a couple of examples. So this is one where you could see that the background music was automatically generated. Now let's look at another example where what you have uh, uh, described is you have just given some text instructions that this is a man in a boat at the sea saying whatever, talking, uh, uh, and this model is able to generate uh, not only kind of that video with all the visuals, but also like reproduce human sound in a very realistic manner, as well as the background sound of waves. Let's take a look.
This ocean, it's a force, a wild, untamed might. And she commands your awe with every breaking light.
So now we are making a tool called Flow, which uses underlying models like VO3, and these tools are now being made available to film studios, to movie producers. And you can see from that last video, right? I mean, it 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 seems like something that could have been shot, right, as an actual filmed video, but it has all automatically generated. Of course, that also raises questions about deep fakes and how do you know excuse How do you know which content is AI generated versus authentic human content? And for that, there has been work done again at Google DeepMind on something called SynthID, which we use to watermark all AI generated content, including it started with images and videos and has been also extended to text. So all uh, output generated by these Gemini models is being automatically watermarked using SynthID uh, based techniques. Now on creativity, let me show you one example of how to help musicians create music. And by the way, I hope this audio part is coming through in when I played these videos. Is it okay?
Yes, sir. Yes, sir.
You're muted.
Yeah, it is fine, sir. We are able to hear clearly.
Sounds
good. Please.
Okay. So let me now show some excerpts from this session that the Google team did with Shankar Mahadevan, right? A well-known music composer in India.
And you kick in the dholak and all, when the roo comes in. Tere aane se da 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 Working with Sandbox was great. We inputted our requirement and it gave us a bed. We used that bed and we came up with this song. Tere aane se roshan hui. It became a beautiful combination of very traditional Sufi melody on a very modern track. I think creating the melody is the most favorite part. When that feeling comes, you really feel proud of yourself.
So again, I mean, what we are doing is taking this approach where we work with artists rather than trying to replace artists. We are trying to provide them tools using AI to help them explore different options, including kind of like generating background music options and so on. So as one of my colleagues likes to say, we are trying to both lift the floor and the ceiling. We are trying to lift the floor that have more of the people at large, right, who are not musicians, who are not like formal, who don't have that mastery in certain forms of art, create better art than we might be able to do on our own. That's lifting the floor, as well as the ceiling, where we work with even experts, even musicians like Shankar Mahadevan, and can we enable them to even do a better job than they might do on their own, or make it easier for them to create beautiful music. With that, let me come to the final topic, which is inclusive AI. How do we develop all of these AI models in a manner that brings benefits to everyone, right, and doesn't create a world of haves and have-nots? So one of the things that we found was that there was a big gap between the quality of these models for a language like English, dominant language like English, and most Indian languages. So our team created this benchmark called Indic GenBench, which was presented at ACL conference last year, where we created over 100,000 benchmarking examples covering problems ranging from cross-lingual question answering, where let's say you are asking the question in Hindi, the original information is in English, and now the response has to be provided to you back in Hindi. Or machine translation, where you're simply asking, let's say, text in English to be translated, let's say, into Kannada. So for a lot of these different kinds of tasks, we did the benchmarking on these tasks for English versus a bundle of 29 Indian languages. And what we saw was, in here again, the higher numbers means better performance, what we saw was every model, including Google's own models, there was a significant gap between the capability of these models on English versus this collection of Indian languages. So what we have been doing is our team has been trying to close that gap, and and I and our first attempt was again about 4 years ago. Our team had built this model called Mural, which at that time provided the largest coverage of Indian languages, 16 Indian languages plus English. And I challenged uh, our team to support all 22 scheduled languages. And then it was very heartening for me to see our lead come back and said that uh, I was not being ambitious enough. So he pointed me to this language survey data, which pointed out that there were 60 Indian languages which are spoken by over 1 million speakers each. And there are 125 languages which have over 1 lakh speakers each in India. So Partha said, let's build a model that understands all of those 125 languages. Easier said than done, because the next thing he told me was that 72 out of these 125 languages were zero corpus languages. That means there was zero known digital data for those languages, which is a bit kind of disappointing, right? For us as Indians, that languages spoken by millions of people have very little digital presence on the open web. And we also know that the same language in India is often spoken in so many different ways. So for those of you who are familiar with Hindi, there's a saying in Hindi called, which says, "Kos kos pe badle pani, char kos par vani," which roughly means that every few kilometers, the taste of water changes in India, and every roughly 10 kilometers, the nature of voice changes. So that particular saying inspired this project called Vani, which we launched together with Indian Institute of Science right here in Bangalore, to start collecting speech data from different corners of India. And we have already made data from the first phase. We have made that data available. It covers 80 districts, over 14,000 hours of audio data, and it spans 59 Indian languages. And 15 of those 59 languages that are covered with this first batch of data used to be those zero corpus languages. So this is the first known digital data available to AI researchers and practitioners for 15 of those languages. And so we are shortly going to make data from phase 2 also freely available. Phase 2 covers even more districts, and in phase 2 we are covering all of the states of India. And in phase 3, our goal is to cover each and every one of the 773 districts of India, so that we hopefully capture the full diversity of languages, dialects, accents, how they're spoken in our country. So as we build these models like Morni, which would understand Indian languages very well, the challenge for our team was, how do we combine the effectiveness of models like Morni on Indian languages with the power of models like Gemini, which earlier, right, I showed you some of the really, really powerful capabilities of a model like Gemini. So how do you get, and Gemini by default didn't understand Indian languages as well, at least before our work, as something like Morni. So our team developed this methodology called CALM, which is a way to automatically compose two language models. This was presented at the iClear conference last year, and where we took a general model like Gemini, and we showed how do you automatically compose it with a specialist model like Morni, which understands Indian languages very well. And the interesting thing is that this approach can be used not just to make a model like Gemini understand Indian languages, it can be made to basically improve Gemini on any domain, let's say clinical domain, where you're building a specialized model that understands the clinical domain very well, or a specialized model that understands code very well. How do you automatically compose it with a generalist model like Gemini? And as we have built these models, what we have seen is that these foundation models are able to do a better job at translation than some of those specialized translate model. And as a result, and since the same model understands hundreds of languages, so in fact, prior to Gemini, we had a model called Palm 2 at Google. So our team created a version of Palm 2 called Palm 2 NTL, which stands for Next 1,000 Languages, which understood over 1,000 languages of the world. And that got used by the Google Translate team last year. They added 110 new languages in one shot to Google Translate, uh, uh, covering languages spoken by over 600 million people. And this was the largest expansion ever of Google Translate. And again, it was this capabilities of these foundation models that enabled this dramatic expansion, because now the same model is understanding all of these hundreds of languages, which brought the number of Indian languages covered by Google Translate to now 28. And last year, in this particular expansion, there were 7 new Indian languages that were added. And we got some very, again, heartwarming kind of inputs from many of the speakers of these languages whose language was included for the first time. The other thing that we have been pointing out is that it's not just enough for a model to understand a new language, a different language. It also needs to understand different cultures. Let's say when you're responding to a user in Assam, we have been making the point that you shouldn't just come up with the response in English and translate that response into Assamese. You should come up with the response rooted in the cultural context of that person in Assam. So this is an area where, again, our team is doing a fair amount of work. We've also created benchmarks like the Cube cultural benchmark that was presented at NeurIPS about a year and a half ago. And we've been coming up with new versions of that benchmark, as well as new methods to improve the capabilities of models like Gemini in understanding different cultures. Quickly, kind of to show some other examples of inclusive AI. Another area where we've been applying AI is to agriculture, which again, there are over 40% of households in India which are dependent on agriculture for their livelihood. And that's an area where we haven't seen as much of benefit from AI as some of the other areas. So our team has built the first such model that, based on satellite imagery, it identifies field boundaries based on usage patterns, and also identifies crops that are being grown. And these models have been made freely available under the Trusted Tester program, covering all of India. And the idea is to build these foundational layers of a digital agri stack, which can then unlock use cases by other startups and other companies which want to build solutions for farmers. So for instance, to provide loan to a farmer. Today, farmers are unable to get loans from formal banking sector because, let's say, the field is some 50 kilometers away from the closest bank branch. The bank doesn't have the kind of the manpower or motivation to send a staff 50 kilometers away to inspect the field and assess the credit worthiness of the farmer. But now, if the bank can, using all of this information at the tip of their fingers, if the bank can assess, okay, what crops the farmer has been growing, what is the expected yield of that crop at harvesting time, and can get a better idea of the credit worthiness of the farmer. So we're trying to enable solutions as well as a lot of the subsidy programs from the government, right? Today, they are not very data driven. We are able to allow all of these insights to be now obtained at a farm level. And to again develop this solution, we needed to overcome several challenges. The spatial challenge, because compared to, we started with models that had been built for farms in North America, and farms in India tend to be much smaller than farms in North America. So there's a need to handle much finer spatial resolution. We have the monsoon season, during which much of the country is covered with clouds, and therefore this RGB spectrum doesn't work very well. So we need to utilize additional spectrum, which is what we have done in our work. We also need finer temporal resolution, right? So when we identify a crop, it's actually much more useful to identify that crop not just after the crop is fully grown and is ready to be harvested, but even early on during the growing season. So this is where we have pushed the temporal boundary. And as I mentioned, all of these models, as of now, are freely available to various startups and so on a test basis for them to try out these models and build solutions. Finally, I'll talk about the efficiency of these LLMs. We all know, kind of a rough rule of thumb was that a query with something like ChatGPT or Google's own Gemini app would cost about 1,000 times more than something like a simple Google search, right? So that was a rough kind of a order of magnitude jump that we saw in the amount of power or cost needed to serve those queries. And what that has led to is we have seen data center energy consumption go through the roof since this whole LLM revolution happened. So our team has been again at the forefront of, we have amongst the best research teams right here in Bangalore, amongst all research teams in the world, which is doing a lot of pioneering work on making these LLMs more efficient. One of our work which has received a lot of recognition and adoption are these elastic transformers models, which we call Matryoshka models. And the name is inspired by Matryoshka nested Russian dolls, which are nested one inside the other. And similar to those Matryoshka nested dolls, we build these models, these Gemini models, in this nested manner. So for instance, when we build a Gemini 16 billion parameter model using this methodology, nested inside that 16 billion parameter model is an 8 billion parameter model, 4 billion, 2 billion, 1 billion, and even a lot of intermediate sizes. And the point of this is that if you have, let's say, a very complex task, you could let your largest model handle that task. But if you have a more intermediate sized problem, like summarize this email, you don't require the most powerful model. You can use a intermediate size model, which would be more efficient. And if you have a really simple query, who's the CEO of Google, who's the Prime Minister of India, you can really get your smallest model to respond to those queries. So this way, just like cloud enable elasticity of compute, we are enabling elasticity of the foundation model power that we bring. The other thing that our team has done is we have looked at all of these different components of an LLM, and we have come up with a series of methods to optimize each of those components. So I'll give you just a very quick idea about some of them. So when you have a query, the response, let's say what are Himalayas, the response that Himalayas are a mountain range and so on, blah, blah, blah. This response is generated today by these state-of-the-art models in a autoregressive manner, which is like one token at a time. And since that autoregressive one token at a time is inherently sequential, this response generation accounts for the bulk of the cost of responding to this query. So our team had this simple idea: can you use a smaller model in tandem with the larger model? So paying attention to the larger model's representation, can you have a smaller model generate the actual output? And this has been again implemented in Google products like Google Gemini app, as well as Google AI Overviews. And it has enabled, so today Google AI Overviews supports over 1 billion users. It has allowed AI Overviews to work with very, very small size model to be able to scale at Google levels when you're serving billions of users. Then the attention layer, right, which is a very powerful part of the of all of these LLMs responsible for its power. But attention, you might know, the complexity of the attention is order n square. If n is the number of tokens, it requires order n square computation. With Treeformer, we create those clusters and then use a decision tree to kind of send it to the right cluster. So we're trying to reduce the complexity of this computation from order n square to close to order n log n. And then there are other operations like softmax computation, where when you're doing an all reduce computation, instead of taking the if you can inexpensively, cheaply kind of predict the top k, the highest, let's say you're doing a max computation over, let's say, millions of numbers. If you can inexpensively predict which are the highest, let's say, top k, and k could be a smaller number, let's say 2048. What are the top 2048 numbers out of those millions of numbers? If you can do that inexpensively, and then you do the max computation only over those 2048 kind of numbers, then you can reduce the cost. So that's the basic idea behind this approach called higher. And through a series of these efficiency improvements that our team has come up with, we have been able to make the Gemini Flash models the most power efficient in the industry. There are some misconceptions in India that DeepSeek brought about a new paradigm and kind of has the highest efficiency, which I've been trying to correct. Gemini Flash models, and I take a lot of pride in our team's work having contributed to the efficiency of these models. Gemini Flash has the highest amount of whatever performance quality per watt or per rupee of any model today. So finally, what I've been talking about is, I mean, sharing with you again a lot of the power of all these AI models. There remain a lot of outstanding challenges, which is, again, I would say there are hundreds of PhDs to be still done addressing many of these challenges. I talked about the challenge of efficiency, and again, we are not done yet. There are, if we compare these models with human brain, right? We often look to human brain as an inspiration. Human brain is able to do all that computation at roughly 20 watts of power consumption, whereas these machines are taking megawatts of power for that same computation. So how do we close that power gap? There's still a lot more work to be done. We all know about the problem of hallucination that these models have. How do you ensure that they are able to stick to facts? how do you make these models more robust and safe? If there are newer kind of problems that you throw at it, which the model is unable to uh, come up with with a good prediction, and this becomes especially important in critical areas like healthcare, where if a model is making predictions about your health condition, uh, it, uh, uh, it should not confidently make kind of bad predictions. Humans typically, uh, when human doctors see a tough case, they they know that this is a tough case, right? And they are then often take care to kind of seek a second opinion and so on. Whereas AI models tend to just kind of go ahead and make a prediction, even if they're wrong. So how do you kind of get these AI models to to better know when they don't know, and do things in a safer manner? How do you get models to avoid perpetuating biases? Again, our team has shown that these models carry not only these biases that have been shown in the Western context, bias based on color, based on uh, gender. Uh, 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 we have shown that these models also carry biases based on other attributes like caste in an Indian context, or religion, and so on. So how do you kind of address those biases? And reasoning still remains, I would say, in my view, an unsolved problem. Yes, today these models are doing very well at a lot of reasoning problems by that chain of thought, uh, and kind of uh, training these models on, again, all kinds of exams and so on, right? Test prep material that these models have seen. But when faced with a completely new problem, these models fail. So we still need some breakthroughs in enabling these models to reason like we humans are able to reason. So with that, let me conclude that AI is already here in a big way, impacting every industry and the world at large. This has been made possible through the rise of foundation models, uh, which have been pre-trained on large amounts of data, and using this generative AI methodology. And and this is especially, I'm envious of all of the students who are going to be entering your careers, right, at this amazing time in history, where you have all of this amazing power of technologies like AI, with computing, backed with sufficient computing power, where you can make a visible dent to any of the challenges, right, that we face as humanity, be it clean energy, be it transportation, be it healthcare, be it finding cures for diseases. Uh, uh, there is clearly that potential for AI to be applied to make to achieve transformative impact. So these are truly exciting times to be living in, because there's this opportunity for you, each and every one of you, to master these technologies and then apply them to solve problems that you are passionate about and make a difference to the world. So with that, let me stop, and happy to take some questions.
Thank you, sir. We have some couple of questions.
Good morning, sir.
Good morning.
Yeah, sir, I need some more information on that neural network, and I need some information on at what stage of that query that neural networks build, and how neural networks builds actually once we need more than two types of data network, like our natural data images and text data, or sometimes like you talk about that some simple queries there we are taking some snaps of that question, and based on that questions that Google Gemini uh, is giving the answers about our Astra learning.
So I didn't. So you're asking about how are these networks, neural networks, built?
At what stage of the queries are actually, and when the sets are more than one, like image, text,
Oh yeah,
videos.
when you have different modalities.
Yeah.
So the way we handle all of these models handle different modalities is there's this process used called tokenization, where the input is broken up into tokens, and these tokens are interleaved. So what happens is when you have text, so if you have this, let's say this text, these are exciting times, you can think of each word, uh, uh, there is some kind of tokenization where maybe the word these would be broken up into two tokens. The first part might be the second part might be SE, or something like R would be a single token. Again, I mean, it varies, but text gets broken up into tokens. Likewise, images. They're also what you create are you take certain parts, portions of the image, and and uh, feed it as a separate token, right? And uh, and likewise, speech also, right, gets broken up into these tokens. And when you have a video, a lot of these different modalities, right, these tokens are in some sense intermingled. So you have the for the video frame, right, you have some part of the video frame that gives you the image tokens from that video frame. Then you have kind of the audio modality. You have tokens covering again the sounds that were uttered in that video. And then you have also, if there is, once you do, if there is transcript available of that video, then you also have the text transcript. So all of these tokens are kind of in some sense intermingled, and then you have this model operating on all of these tokens. So it is taking those as input tokens, and then it is again producing an output, which is also in the form of those different tokens. So I don't know if I answered your question.
Sir, is it dynamic or like for a one query, one
So
neural?
what you do, so what you do is you train a network first on pre-trained data using self-supervision, right? So a lot of times you are just predicting the next token. The self-supervised learning task, when you are training those networks, you are given a stream of data. You just tokenize it, and you ask the network, you train the network to predict the next token. And you already know what that next token is, right? Because you have that entire data. So what you do is there is a pre-training stage where you build this network and you train it on that all of that data using the self-supervised learning methods. Now, in these modern models, after that pre-training stage, there is another step called supervised fine-tuning, where you fine-tune it with some high-quality labeled data. And then there is a phase called RLHF, where you do reinforcement learning based on human feedback, where you kind of feed it some examples. For instance, here's a query, and here are two sample responses, and you have human who rates which of those two responses are better. And that reinforcement learning based on that human feedback is used to again help improve the model. So I've glossed over some of those differences, some of those details. So there's a whole step starting with pre-training, supervised fine-tuning, and then reinforcement learning that is done to build these models. And once this model is built, now on any input, right, which is given, let's say your query is given, now this model is just doing that computation based on its weights that are already assigned based on that training. Did I answer your question?
Thank you, sir.
Sir, that agricultural model you told, you have used a different spectrum other than optical. Did you use microwave, that is radar, C-band, L-band, or
Yeah, so I
X-band.
know they have used the SAR, synthetic aperture radar.
Yeah.
I have to check on what all are the different
Because
spectrum.
they are not amenable. They are not amenable for either supervised classification or unsupervised classification. So I have a doubt whether you scaled it up or scaled down properly, because we go for a different type of classification techniques for microwave. It is very tough.
Yeah.
We have tried with X-band as well as C-band to identify the crops. It is a nightmare for us still.
Sure.
So I just want to learn from how many PhDs are over in that so far.
So I'm happy to connect you with our team that has been developing those models.
Okay, thank you.
Good morning, sir.
Good morning.
In your product like Imagen 4 and Vivo 3, when I create any image or video, whether it is copyright issue will comes.
Yeah, so that's a great question. So one is the question, what have you used copyrighted data, right, to train those models? And Google has a very conscious approach of when we use kind of material from artists and so on, Google pays those artists, right, to make use and gets their consent, right, to use copyrighted data. This is a subject of also today, there's still lack of clarity on what is, because copyright law also permits something called fair use. So what is considered fair use, what is not? This is still being decided in different courts and being decided very differently. So for instance, Japan has issued a law that provides a blanket approval to AI models to use any kind of copyrighted data to create those models. So Japan has gone to that extreme. Recently, there was a court case in which the US court kind of ruled in favor of Anthropic, where Anthropic was making use of some copyrighted data without compensating the creators of that copyrighted data. But the US court ruled that the use by Anthropic to create those models was still under fair use. So this is still a topic of a lot of debate. So one is that what kind of copyrighted data has been used to train those models. The other aspect is, as you produce the output, are you marking that data? So Google is taking the approach that there is digital watermarking being done of all of these outputs from VO3, Imagen 4 models with SynthID.
Yes, sir. Thank you. And another question is, you told that at the end of the session, related with a medical response, like you are using some model to predict the disease. Why can't you mention the result is of this much accuracy? It may be helpful for the doctors, because the models is showing
that's a great question. The problem is that unlike humans, right, who have an inherent understanding that this is an easy case versus this is a tough case, the AI models today using this deep learning approach are not usually able to do a very good calibration of estimating their certainty about the output. So they could be uncertain about cases where they are right, and they could be quite certain about cases where they are wrong. So that's the problem of calibration that I was mentioning as an open challenge still.
Sir, another question. What is the concern about societal issue? Because you have developed a lot of AI model. When someone is uploading a non-ethical or the text or video is nowhere has a authentication, why can't you block automatically when uploading? Do you have any solution from your side?
Yeah, so there are solutions that are now the question is, what do you mean? What is the kind of content, right, that should be blocked? Is it AI generated content that should be blocked, or is it unethical? And unethical in what ways? Is it videos showing violence? Is it videos showing misinformation? So there are a lot of different kind of, even this is a tricky policy question of what is considered uh, uh, what is considered acceptable versus non-acceptable, because there are also different standards on freedom of speech that different countries apply. So this is not a very simple process, right, in terms of even human decision making of which video should be blocked and which one should not be.
Okay, sir. Thank
I come from a college which may not have the resources to subscribe to all top international journals, but at least is there a opportunity to access all the research work done by Google scientists at one place?
The usual place is just the web, right? The conferences where our researchers also publish. So the usual conferences, NeurIPS, ICML, ICLR, a lot of these conferences where we publish.
Maybe this question is for a larger audience.
There's also archive, right? So archive is a great source of a lot of research publications.
I'll repeat these questions. I find it difficult to access papers, important papers, unless you have subscribed them or you belong to a top institution. So is there one place where Google's work is available?
So archive is a source which is freely available to everyone, and a lot of Google papers go into archive.
Okay, thank you.
Hello, sir. I'm Sujit here. Thank you for this nice, beautiful presentation. I have many questions in my mind, but if you are kind enough, you can give your mail ID or phone number to get in touch. But for the time being, I'll ask you two questions. Sir, one, in that Astra, you told, a student can learn many things, he can, get the answer. But will it not hamper the collaboration and the study together, asking your doubts to other fellow may give you something else, and in the process of asking one doubt you'll get 10 answers. Will it not hamper that?
No, that's a great observation and a great question. So with Astra, there is a research project called Hypatia, where the team is attempting to tackle precisely the problem that you point out, right? That the AI model may know what the answer is, right, to a question. Now, if it just gives away the answer to the student, it is going to hamper learning. Instead of giving away the answer, right, can you nudge the student towards finding the answer themselves? And you saw in that particular demo video, right, it wasn't just giving the student the answer. It was kind of saying, okay, why don't you solve the problem, right? And then while the student was facing issues solving the problem, it was providing some hints, and then it asked the student to come up with its solution, and then it was pointing out where the solution had some mistakes. So again, these are techniques being that have been implemented to try and address, right, the problem that you pointed out. Now, is it perfect? I wouldn't claim, no, it's perfect at this point, but these are attempts being made to kind of use principles of pedagogy in building these tools instead of kind of just a model that gives you the answer.
Yeah, somewhat answered, but I'll just give an example. When mobiles came, people before mobile age, I would say, people are more collaborative. Once mobile comes, and now you see anywhere you go, people are watching their mobiles rather than gossiping. So it hampered. Still, we're saying, you accept the technology, that is fine, and even we'll accept the AI also, but definitely it will hamper the the things which we are doing right now.
I agree. There are certain aspects that one has to be careful about, which can lead to harmful effects of the same technology. Agree with your basic point, but again, it's a debatable point. I mean, should you not build that technology at all, or should you be more careful about how to use that technology, right? So that's where I feel we have to be more careful in how we use the technologies.
True. So, but I never saw anywhere, any of the presentation, anything, not here, anywhere, people are not saying how to use the AI. They're just saying AI will do this thing, that thing is good. Even I accept that. I am also using it. But, it's not spreading, how to
Yeah.
use the AI.
No, it's a valid point.
And my second query is, sir, I used to, make a project in Excel, Google spreadsheet. I asked one of my doubt, I have to skip the Sunday, in the date format, I have to skip the Sunday and I have to roll it down to Monday to Saturday for a year or 2 years. I asked that query, how to get over it to all three, ChatGPT, Gemini, Copilot. The best answer I got, I thought I'll get it from Gemini, but I got it from ChatGPT. And I thought Copilot also will give. It didn't give me any answer, even though it's a Microsoft Excel. So that's what.
Yeah. See, through today, look, there are all kinds of queries where you will get the best answer from a different model depending on. So yeah, I mean, there remains right a lot of variation. I mean, there are all kinds of other tests that have been done which show sometimes Anthropic doing much better, ChatGPT failing miserably. So there are a lot of these different kinds of things, right? So a lot of that benchmarking is being done. So I have to unfortunately run. I have to go to my next meeting. So is it okay if we?
Yeah. Thank you, sir.